So guys, in this chapter, we're going to cover the kinematics of a rigid body like we did for a particle. But here we have a rigid body, and the difference between rigid body and a particle, as we said in the video lecture, is that a rigid body is in fact a set of particles. I cannot neglect the size of a rigid body like I did for a particle. And as I said in the video lecture, there are three types of motion for a rigid body. I can have a translation, but in this case, in the translation, the vector AB would be always constant in vector. All right, so AB vector will be equal to a constant vector, and this means that the velocity of all the points inside this rigid body will have the same velocity as well as the same acceleration. Now, the second type of motion is the rotation, and in this case, guys, if I have a rotation, then the vector AB will not be the same because the direction will differ here. And what you have to know, guys, that if I have a fixed point and this point belongs to the axis of rotation, I can find the velocity of any other point by doing omega cross r. Now, if I have a plane, a general plane motion, in this case, I'm going to have a rotation as well as a translation. And guys, the key to solve such a problem is to apply the relative position or the relative velocity, because from the relative velocity, which is here, for example, VB is equal to VA plus dRBA over dt, I can find, in fact, two equations to unknowns, because I can translate this equation into I and j. All right, and also, guys, I want you to know that all the equations that are proved in kinematics for a particle are also applied for kinematics of a rigid body, and I can, in fact, do the analogy. So if you want to do the analogy, in fact, you can replace S by theta. You can replace V by omega, and you can replace A by alpha. And this is the analogy between a translation and rotation, and then you can have the equation of kinematics for the velocity, for the acceleration in the cases of constant velocity, constant acceleration, and the independent equation of time for velocity if I have a constant acceleration. So they are all the same, guys. They are all the same, except that you have to substitute S by theta, V by omega, and A by alpha. And then we proved in the equation of a rigid body that if I have a pure rotation, V will be equal to omega cross R. And since omega and R, they are perpendicular, then V in module will be omega R. And then the normal acceleration would be equal to omega squared R. And then the tangential acceleration will be equal to alpha times R. So let's start by the first example here. This is the example of kinematics for a rotating rigid body. So I have here a disk that is originally rotating at omega 0 is equal to 12 radians per second. So I know the initial angular velocity for this disk. It's subjected to a constant angular acceleration, alpha. So alpha is constant. This is a very important note. And I need to determine the magnitude of the velocity. So I need to determine V, what is V? As well as I need to determine the components, normal and tangential of acceleration at point B. So I need to determine, in fact, VB, and this is point B, far from the center of rotation by 0.4. As well as I need to determine alpha B tangential and alpha B normal. Right? Knowing that alpha is equal to constant and it's equal to 20 radians per second. The question is to determine alpha BT, alpha B, and VB when the disk undergoes 2 revolutions. What is this 2 revolution, guys? Is it the time? Or is it what? Who can tell me, guys? What is this 2 revolutions? It is theta. Perfect, Abbas. Yes. So theta is equal to 2 revolutions, which means it's equal to 2 times 2 pi radians. It's 4 pi radians. Alright, guys? Now, how to find VB? What do you think, guys? Or how to find, first of all, omega? Because if I know omega, I can find VB. VB is omega times RB. So how can I find omega, guys? What equation should I use to find omega if I know that alpha is constant, omega 0 is 12, and theta is equal to 4 pi? What do you think? What equation should I use? What do you think, guys? What equation should I use? Alpha is constant. This means that this is a uniformly accelerated rotation. I know the initial angular velocity omega 0, and I know theta. Yes, the independent equation of time. Perfect, Noor. So I have to use the independent equation of time for omega. Remember, in the general plane motion for a particle, if I have a constant acceleration, I can apply the independent equation of time for v. Now here I need to apply it for omega, right? So omega squared is equal to omega 0 squared, because I know omega 0, plus 2 alpha theta minus theta 0. Right, guys? Now, what is omega? Omega squared is what I need to find. What is omega 0? It's given, it's a 12. So 12 squared plus 2. What is alpha? It's 20. So plus 40 times 4 pi minus 0. Alright, so I can find omega now. Omega will be equal to 24.5 radians per second. 25.4, sorry. Alright. Now that I know omega, I can find what? I can find VB. So what is VB, guys? VB is equal in module or in magnitude to omega times RB. Let's go back to the figure to find RB. RB is equal to what? To 0.5. Now, if I want to find it for A, RA is 0.5. Now, here, since I need to find it for B, so it's 0.4, all right? So it's 25.4 times 0.4. And this is, guys, because this is a rotational motion, right? So this is a pure rotation. Any point here has a velocity that is equal to omega of this disk at this instant times the radius, right? So as you can see, there is a difference between rotation and translation. If this is a translation, all the points will have the same velocity, but since this is a rotational motion, then the velocity will be equal to omega times r, all right? So, which is about 10.17 meters per second. And now if I want to find the acceleration, this is the acceleration. I'm going to have two acceleration. The normal acceleration, which is in vector equal to minus omega squared times r. In magnitude, it's omega squared r. V, of course, because I'm finding this acceleration in B. So it is 25.4 squared times 0.4, which is about 259 meters per second squared. And now A tangential will be equal to alpha times RB, right? And this stands, of course, for the change in the velocity magnitude, while this stands for the change of the direction. So it's a 20 times 0.4, which is, of course, 8 meters per second squared. All right? So as you can see, guys, if I have a pure rotation, all the equations for kinematics could be applied here for alpha and omega by substituting S by theta, V by omega, and A by alpha. And then the points on this disk will have different velocity and acceleration depending on their radius. right? Or depending on the distance from the point of rotation, which is here the center of the disk, to the point considered. All right, guys? So this is a very easy example. Do you have any question? Do you have any question, guys? Okay.